Hidden inside a distant galaxy known as LRG 37537 lies one of the heaviest black holes ever discovered, weighing billions of times more than our Sun. How can such an immense object even exist? And what does it mean for the universe around it? Stay with us as we uncover this cosmic giant. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, do you think there could be black holes even bigger than this? Thank you for watching. Now let's begin. In the distant fabric of the universe, vast structures of matter are arranged like threads woven into a cosmic web. Galaxies are not scattered randomly, but lie along filaments of dark matter that span hundreds of millions of light years. These filaments connect to each other, forming nodes where gravity has pulled together countless galaxies' clusters and immense halos of unseen material. Between them stretch enormous voids, regions that appear almost empty when compared to the glowing chains of matter. This pattern emerged gradually over billions of years as gravity amplified small variations that once rippled through a hot, nearly uniform early cosmos. Today, telescopes trace these patterns across the sky, showing that galaxies are the bright signposts of deeper structures that remain hidden. In such a web, matter is not only luminous, but also invisible, with the unseen component outweighing the visible. Dark matter, which does not emit or absorb light, supplies the underlying scaffolding on which galaxies are built. Its gravity controls the motions of stars and galaxies alike, and its presence is revealed only by its effect on ordinary matter. Cosmological surveys show that dark matter outweighs visible matter by more than 5 to 1, and its distribution determines the layout of the cosmic landscape. Observations from satellites like the Planck mission reveal that this architecture took shape soon after the Big Bang, with the early distribution of matter setting the stage for all subsequent evolution. Clusters of galaxies form at the densest nodes of this cosmic web. They are immense concentrations of matter, each containing thousands of galaxies bound by gravity, with masses equivalent to quadrillions of suns. Between their galaxies lies hot gas that glows in X-rays, and enormous envelopes of dark matter that cannot be seen directly. These clusters are among the most massive structures in the universe, and their gravitational influence extends for millions of light years in every direction. Within clusters, galaxies experience tidal forces, collisions and mergers, shaping their forms and sometimes fueling activity in their centers. The cluster environment is harsh, stripping galaxies of their gas and leaving many of them as smooth elliptical systems dominated by old stars. The density of such places makes them laboratories for extreme astrophysical processes, from shock waves in intracluster gas to bursts of star formation triggered by encounters. Among these structures there are smaller groupings as well. Not all galaxies reside in such massive clusters. Many exist in loose groups containing only a few members. These groups, while less massive than clusters, also reflect the cosmic web's underlying framework. They serve as environments where galaxies can still interact, merge and evolve, but on less extreme scales. It is in such regions that gravitational lensing sometimes reveals itself most strikingly. When a massive galaxy lies along the line of sight to a more distant one, its gravity bends and magnifies the light of the background source. This bending is not due to a physical obstruction, but to the curvature of space-time itself, a direct consequence of general relativity. The result is that light follows curved paths, producing arcs, rings, and multiple images that would not otherwise exist. These distorted shapes allow astronomers to measure the mass of the intervening galaxy with remarkable precision, including the contribution from dark matter that would otherwise remain invisible. Such lensing events are rare and striking. They appear as curved arcs of light surrounding a central galaxy evidence of gravity's profound effect on the path of photons travelling across billions of years. The precise configuration depends on the alignment between observer lens and background source, as well as the mass distribution of the lensing object. When alignment is nearly perfect, the background light can form nearly complete circles known as Einstein rings. Even when not fully circular, the arcs they create can be large and bright enough to be studied in detail. These phenomena not only reveal the total mass of the lensing galaxy, but also magnify distant galaxies that would otherwise be too faint to study. Through them, astronomers peer deeper into cosmic history, viewing galaxies in their early stages of formation. Within this grand context, the system known as LRG 3757 resides. It lies as one participant in the intricate cosmic tapestry, distinguished by its extraordinary gravitational influence. It is not alone in its region of space, but connected to the web of matter that stretches across the cosmos. The arcs of light around it are not random shapes, but the visible trace of curved space-time, a direct indicator of the immense mass it contains. Though only one among many galaxies, it stands out because of the scale of the bending it produces. From Earth, the distorted light is captured by instruments capable of detecting the faint glow of distant sources, allowing astronomers to reconstruct the mass distribution with clarity. At the scale of billions of light-years distances blur human intuition. Light that arrives today from the lensed background galaxies began its journey when the universe was much younger, crossing expanding space before being diverted by the gravity of the intervening system. This time depth means that what is seen is a combination of multiple epochs, the lensing galaxy as it was billions of years ago, and the background galaxy as it appeared even earlier. Lensing in this sense is both a window into the distribution of mass and a time machine reaching back into early cosmic eras. In the case of this particular system, the arcs form a near-complete ring often referred to as a cosmic horseshoe, an image that has captured attention not for symbolism but for its rarity. Few alignments in the observable sky produce such striking and symmetric patterns. The study of such a lens requires careful observation. Surveys that chart wide areas of the sky look for candidates, and once an unusual arc is spotted, follow up with higher resolution imaging refines the picture. The arcs are modelled using equations of general relativity, allowing astronomers to map the distribution of matter in the lensing galaxy. This method is particularly valuable because it does not rely on light emitted by the galaxy itself. Instead, it depends on the way mass warps the paths of photons. In this way, lensing becomes one of the most direct tools for measuring the total mass of galaxies, including both visible and invisible components. When the light paths are mapped, the extent of the bending reveals the true scale of the galaxy's gravitational field. For ordinary galaxies, arcs are faint and small. For massive ellipticals like LRG 3757, the arcs extend broadly, indicating not just a concentration of stars, but an underlying reservoir of dark matter, and in the centre something far denser still. The distribution can be reconstructed as a profile of increasing density toward the core. Each layer of mass contributes to the overall curvature of space, guiding the background light into its observed shapes. As a result, even without directly seeing the innermost engine, astronomers can infer its presence from the way space itself is curved around it. At the scale of cosmology, this galaxy is one among billions, yet the depth of its gravitational imprint makes it stand out in the survey data. The horseshoe-shaped arc is not just visually striking, but scientifically significant. It shows that gravity here is exceptionally strong, requiring an immense concentration of matter. In the background, faint galaxies serve as light sources, but the true story is the foreground system that bends them. From this starting point, the exploration of its structure and the extraordinary black hole at its core begins layer by layer, always moving inward from the broadest context toward the central heart of gravity. Across the larger neighborhoods of the universe, galaxies do not exist in isolation, but as members of groups and clusters. These associations range in scale from small gatherings of only a few galaxies to vast collections numbering in the thousands. The clustering of galaxies arises from the distribution of dark matter, whose gravitational field gathers luminous matter into the nodes of the cosmic web. As a result, the universe presents an intricate hierarchy. Filaments feed material into groups, groups assemble into clusters, and clusters sometimes merge to form even larger superclusters. In these environments, galaxies are subjected to complex interactions that shape their structure and fate. Gas is stripped from them as they move through hot intracluster plasma, while their stellar halos are distorted by gravitational encounters. Over cosmic time, many galaxies lose their spiral arms and settle into more featureless ellipses, their stars orbiting in random directions instead of the orderly rotation of a disk. In the regions where matter collects most densely, the gravitational potential wells are deep enough to trap gas at temperatures of tens of millions of degrees Kelvin. Such hot plasma fills the spaces between galaxies, emitting X-rays detectable by space-based observatories. These observations show that a large fraction of the baryonic matter in clusters is not in stars but in diffuse gas. The gravitational field of dark matter confines this gas, preventing it from escaping despite its high temperature. The combined presence of galaxies' plasma and dark matter creates some of the largest bound structures in the universe. The scale of these systems is measured not in millions, but in tens of millions of light-years across, and their total mass can exceed 1,000,000 billion times the mass of the Sun. The galaxies within them are bound together in a gravitational dance, their paths influenced by the combined mass of all members. In such a setting, the lensing system known as LRG 3757 has its place. Its arcs and distortions reveal that it lies within an environment where mass is unusually concentrated. The host galaxy itself dominates its local surroundings, but the context of its neighborhood adds to the total field. Galaxies that lie nearby contribute to the bending of light, even if only slightly. Astronomers account for this by modelling not just the mass of the central galaxy, but also the distribution of matter in its environment. This makes gravitational lensing both a challenge and an opportunity. While complex to disentangle it, allows for detailed mapping of mass over a wide area. The result is a layered view in which the central system emerges as a dominant peak atop a broader landscape of matter. The environment of massive galaxies in groups or clusters has further consequences. Their interactions strip them of cold gas, leaving them unable to form many new stars. Their colours shift toward the red, reflecting populations of older, cooler stars that dominate their light. Over billions of years, repeated encounters smooth their structures into the rounded forms typical of elliptical galaxies. Many such systems harbour central black holes, whose masses correlate with the properties of their host galaxies, suggesting a shared evolutionary history. The largest galaxies, often found at the centres of clusters, contain the most massive black holes. This pattern indicates that galaxy growth through mergers and black hole growth through accretion are connected processes, each feeding into the other over time. Clusters are also dynamic environments where subclusters fall together and merge, creating shocks in the intracluster gas and stirring up turbulence. These collisions can last for hundreds of millions of years, during which galaxies are thrown into new orbits and gas is redistributed. The evidence of these processes can be seen in radio observations that detect extended relics and halos. signatures of particles accelerated in cluster-scale shocks. These environments are extreme laboratories for the study of gravity gas dynamics and particle physics. For the galaxies within them, the long-term result is transformation, and sometimes destruction, as smaller galaxies are absorbed into larger ones. Measurements of the motions of galaxies within clusters provide direct evidence for the presence of dark matter. The speeds at which galaxies move are far too high to be explained by the gravity of visible matter alone. Similarly, the temperature of the intracluster gas requires additional mass to confine it. Gravitational lensing offers a third line of evidence independent of both. Together, these methods converge on the conclusion that clusters are overwhelmingly dominated by dark matter. This invisible component is not a minor addition, but the main contributor to their mass budget. In this sense, visible galaxies are tracers floating in a much larger and heavier sea of unseen matter. When examining the neighborhood of the lensing system, astronomers consider both the large-scale environment and the local context. Isolated galaxies can act as lenses, but those embedded in denser regions produce more complex patterns. The lensing arcs of LRG 3757 appear symmetric enough to suggest that the mass distribution is dominated by the central galaxy itself, rather than a complex interplay of many nearby ones. Even so, the broader neighborhood cannot be ignored. It establishes the stage upon which the central galaxy has grown to its present size, accumulating mass through the gradual merger of smaller systems. Each collision would have brought not only stars but also central black holes, which eventually sank to the core and merged into a single larger one. Over billions of years, such processes created the massive elliptical galaxy visible today. In cosmological terms, these structures are not static. Clusters continue to grow as material flows along filaments of the cosmic web. New galaxies fall inward, adding their mass to the central system. The universe itself expands, stretching the distances between superclusters, but gravity holds these dense knots together. Within them, time seems to slow relative to the overall expansion, as their internal gravity dominates over the cosmological background. This means that the environments where the largest black holes are found are also those most resistant to the universe's stretching fabric. They are anchored places massive enough to maintain their coherence, even as the cosmos at large grows ever more diffuse. The larger neighborhood of this particular system can thus be seen as both cradle and container. It supplied the raw material for the galaxy's assembly and continues to hold it in a gravitational grip. The arcs of light serve as proof of the density of the region, while the stellar population of the host speaks to the long evolutionary path it has followed. Step by step, from the broadest web of filaments to the densest knots of mass, the stage is set for the remarkable concentration of matter found at the core. From here, the journey continues inward, narrowing from neighborhood scales to the distinctive lensing features that first drew attention to the system. The discovery of unusual systems in the sky often begins with surveys that scan wide areas in search of faint structures. These surveys, conducted with ground-based and space-based instruments, create catalogues of galaxies by capturing their light across multiple wavelengths. By analyzing these catalogues, astronomers identify candidates that stand out for their brightness, shape, or unusual alignment with background objects. One such system revealed itself through the peculiar bending of light, its image differing from the typical forms of elliptical galaxies. The arcs encircling it marked it immediately as a gravitational lens. What distinguished it further was the symmetry and brightness of the arc, suggesting not only a significant mass, but also a rare alignment with a distant background source. Such alignments are not common for the positions of foreground galaxies, background galaxies, and Earth-based observers must line up precisely. When they do, the result is an optical signature that cannot be mistaken for anything else. This is how the system known as LRG 3757 entered scientific awareness. Its detection came through a survey designed not for beauty, but for completeness, seeking to map galaxies over wide stretches of the sky. The acronym LRG refers to luminous red galaxies, a category of galaxies used in large-scale structure studies because of their brightness and uniform properties. Their red color indicates old stellar populations, and their luminosity makes them visible across great distances. By including such galaxies in catalogues, astronomers trace the underlying distribution of matter, mapping how galaxies cluster together and form filaments. Amid these catalogues, the galaxy in question revealed its gravitational effect through the arcs of light wrapped around it. Follow-up observations confirmed the presence of the lensing arc and established its nearly complete horseshoe shape. This geometry is produced when the lens is massive and the alignment is close to perfect. The background source, lying billions of light-years farther away, is stretched and magnified, forming the bright arc visible in imaging data. Spectroscopy can then determine the redshift of both lens and source, providing distances and allowing astronomers to model the mass distribution of the lensing galaxy. With this information, the system became more than just an entry in a catalogue. It became an important case study for the measurement of extreme galactic mass. The role of surveys in such discoveries cannot be overstated. Wide-field instruments like the Sloan Digital Sky Survey and its successors have provided maps of millions of galaxies, enabling statistical studies and rare finds alike. Gravitational lenses like the horseshoe formed by this galaxy serve as natural telescopes magnifying distant galaxies that would otherwise remain unseen. They also provide a way to measure the mass of the lens itself without relying solely on the light it emits. In this case, the strength of the lensing revealed that the central galaxy contained far more mass than its starlight alone could account for. The arcs demanded an explanation rooted in gravity, not in luminous emission. The discovery phase also involved attention to detail. Identifying lensing arcs requires distinguishing them from other elongated features such as tidal streams or coincidental alignments of galaxies. Careful inspection of color images and spectra confirmed that the arc light had a different redshift than the foreground galaxy, proving that it originated from a much more distant source. The curvature of the arc further supported the interpretation of lensing, as only gravitational deflection produces the symmetry seen. By excluding other possibilities, astronomers were left with the clear conclusion that this system acted as a gravitational lens of unusual power. Once confirmed, the system became a target for deeper imaging. High-resolution telescopes, both ground-based with adaptive optics and space-based without atmospheric distortion, refined the view of the arc. The clarity of these observations allowed detailed modelling of the mass distribution. Instead of a vague estimate, astronomers could reconstruct the profile of the lens, identifying how mass increased toward the centre and how it extended outward into a broad halo. These models provided not just a number for the total mass, but also a map of how that mass was arranged. The results placed the galaxy among the most massive lenses known, with an inner core dense enough to suggest the presence of an extraordinary central black hole. Gravitational lensing discoveries are often celebrated for their visual appeal, with arcs and rings resembling shapes familiar to the human eye. Yet their scientific value lies in what they reveal about the otherwise invisible. Lenses expose dark matter, halos confirm general relativity across cosmic distances, and enable the study of galaxies too faint to observe directly. The case of the Cosmic Horseshoe created by LRG 3757 demonstrates each of these. It shows the strength of gravity in action, the reliability of Einstein's theory, and the scale of galactic mass that can be hidden beneath the glow of stars. The detection process also underscores the importance of alignment. The universe is filled with galaxies at many distances, yet only rarely do they line up so precisely that one can lens the other into such a dramatic shape. When such alignments occur, they are treasured opportunities. They allow scientists to probe both the lens and the source, simultaneously yielding information about two separate galaxies in one observation. The lens provides data on mass distribution, while the lensed source can be magnified enough to reveal details of its structure and star formation history. In this way, gravitational lensing is a dual probe useful for studying both the foreground and the background. In the broader scope of astrophysics, each new strong lens discovered expands the sample available for statistical study. With a larger set, patterns emerge about how galaxies of different types and masses act as lenses. The particularly strong lensing produced by the galaxy in question adds to the high mass end of this distribution, helping to constrain models of galaxy formation and evolution. It shows that some galaxies, through mergers and accretion, can reach masses far beyond the norm, their gravity bending light into nearly complete rings. The recognition of this system as a lens and the subsequent modelling of its properties mark the beginning of a deeper investigation into its structure. What started as an entry in a survey catalogue evolved into one of the most striking lensing examples in the sky. Each observation peeled back another layer from identification to confirmation to detailed modelling. The result is not only a beautiful image but also a profound insight into the nature of mass in the universe. Step by step, astronomers built the case that the system is among the heaviest galaxies ever observed, setting the stage for further exploration of its inner regions and the extraordinary concentration of matter at its centre. When light from a distant galaxy passes near a massive object, its path curves, and the image seen from Earth becomes distorted. This effect, predicted by general relativity, is known as gravitational lensing. In the case of certain galaxies, the lensing is strong enough to create elongated arcs, multiple images, or even rings of light. Such structures are not artistic impressions, but genuine deflections produced by gravity. They allow astronomers to measure the total mass of the lensing galaxy with extraordinary precision, because the geometry of the arcs is directly linked to the strength of the gravitational field. Among the known lenses, a few stand out for the clarity and completeness of their arcs. One of these is the system that creates a nearly circular horseshoe of light, a rare and vivid demonstration of the scale of cosmic gravity. The arcs encircling this system are formed by the light of a background galaxy located far beyond the lens. As the light travels for billions of years across expanding space, it encounters the gravitational field of the foreground galaxy. Instead of travelling straight, the photons follow curved paths wrapping around the lens and arriving at Earth as bent streams. Depending on the alignment, these paths can combine to form partial arcs or closed rings. In this case, the near-perfect alignment produces a striking arc that nearly completes a circle. The luminous curve contrasts against the dark of the sky, outlining the otherwise invisible field of gravity. Its symmetry provides a rare opportunity for measurement, since any departure from a perfect circle carries information about the distribution of mass within the lens. Detailed imaging of the horseshoe arc shows subtle variations in brightness and curvature. These variations are used in lensing models to reconstruct the profile of the lensing galaxy. By adjusting parameters such as mass density, slope, and ellipticity, astronomers reproduce the observed arc and thereby infer the actual structure of the mass distribution. This is not a guess, but a rigorous calculation constrained by the rules of general relativity and the observed data. The outcome shows that the central galaxy is immensely massive with its gravity bending light over a wide area. The arc does not merely surround the visible galaxy, but extends outward, showing that dark matter plays a dominant role in shaping the field. The luminous horseshoe is thus both an aesthetic image and a map of invisible mass. The brightness of the lensed arc is also valuable. Because gravitational lensing magnifies background sources, the distant galaxy appears brighter than it would without the lens. This allows astronomers to study its properties even though it lies billions of light years away. In effect, the lensing galaxy acts as a natural telescope, amplifying the signal of a faint background source. This dual role makes lensing systems doubly important. They reveal the mass of the lens, and they provide access to the light of galaxies otherwise too distant to examine. In this way, a single observation yields insights into two epochs of cosmic history, separated by billions of years. The horseshoe arc has become one of the most recognizable examples of strong gravitational lensing. Its geometry is used in educational materials to illustrate the principles of general relativity, while its detailed analysis provides data for professional research. What sets it apart is not only the completeness of the arc, but also the clarity of its symmetry. Many lensing systems show partial arcs or multiple images, but few produce such a nearly continuous curve. This rarity underscores the fortunate alignment of lens source and observer. It is a cosmic coincidence, and yet within a universe of hundreds of billions of galaxies, such coincidences are inevitable somewhere. This particular one has offered an especially clear window into the mass distribution of the lensing galaxy. The role of lensing arcs in mapping dark matter is profound. Unlike visible matter, dark matter does not emit, absorb, or reflect light. Its existence is inferred entirely through its gravitational influence. Gravitational lensing is one of the few direct probes of this invisible component. By comparing the shape of arcs with the distribution of visible stars, astronomers can determine how much mass is dark and how much is luminous. In the case of the horseshoe, the mass required to produce the observed arc far exceeds the contribution of stars alone. The lensing signal therefore reveals an extended halo of dark matter surrounding the galaxy, stretching far beyond the visible light. This finding is consistent with other studies of galaxies and clusters, but in this case the clarity of the arc makes the conclusion particularly robust. The geometry of the arc also gives insight into the shape of the dark matter halo. If the halo were perfectly spherical, the arc would form a near-perfect circle. Deviations from circularity indicate elongation or asymmetry in the mass distribution. By fitting these details, astronomers reconstruct the three-dimensional shape of the halo, learning how dark matter is arranged on galactic scales. This information is critical for testing cosmological models, which predict not only the amount of dark matter, but also its clustering properties. The horseshoe lens thus contributes to the broader effort of understanding the fundamental structure of the universe. Beyond dark matter, the arcs also shed light on the luminous content of the lensing galaxy. The stars in the central galaxy contribute to the overall mass profile, especially near the core. By combining lensing measurements with stellar population studies, astronomers separate the contributions of stars' gas and dark matter. This multi-pronged approach refines estimates of the total mass and the relative proportions of its components. In the case of very massive galaxies, the stellar contribution becomes small compared to the dark matter halo and the central black hole. The horseshoe arc points clearly to this outcome. The galaxy is dominated by unseen matter, with stars only providing a fraction of the mass needed to explain the deflection. The arcs are more than a scientific tool. They are a reminder of the scale of cosmic distances. The light forming the horseshoe left its source when the universe was much younger, perhaps less than half its current age. During that time, it crossed expanding space, was bent by a foreground galaxy, and then continued to Earth. By the time it reached telescopes, billions of years had passed. What is seen in the arc is therefore a record of two galaxies at different times, one closer, one farther, their relationship revealed by gravity alone. This blending of time and space is a hallmark of astronomy, where every observation is a look back across epochs. In studying the Horseshoe Arc, astronomers have not only confirmed the immense mass of the Lensing galaxy, but also strengthened the evidence for the presence of one of the heaviest black holes ever measured. The arc, while only a feature of distorted background light, is a gateway to understanding the unseen. Its presence confirms the galaxy's mass, its shape refines models of dark matter, and its brightness allows the study of a background system. From the outer arcs of light, the path now moves inward toward the host galaxy itself, where the concentration of mass becomes even more apparent. At the heart of every gravitational lens is the lensing object itself, the galaxy whose mass bends light and shapes arcs into the sky. In the case of the system producing the Horseshoe Arc, the central galaxy is a luminous elliptical massive enough to dominate its surroundings. Elliptical galaxies differ markedly from spirals. They lack the grand arms of star formation, the disks of cold gas, and the prominent dust lanes that give spirals their layered appearance. Instead, ellipticals are smooth and rounded, their light distributed more evenly, with stars moving in many directions rather than ordered rotation. Their populations are old, made up largely of low-mass, long-lived stars that have burned steadily for billions of years. The absence of cold gas means that new stars form only rarely, and the overall colour of the galaxy is reddish, the hallmark of an ancient stellar assembly. The host of the Cosmic Horseshoe is a giant elliptical galaxy, one of the largest kinds known. Such galaxies are typically found in dense environments, often at the centres of groups or clusters, where they have grown through repeated mergers. Each merger brings in more stars and sometimes funnels gas to the centre, where it can feed a central black hole. Over billions of years, this process builds galaxies with masses far greater than those of typical spirals. Their stellar halos extend far into space, their density dropping gradually outward, blending into the dark matter halo that envelops them. The galaxy producing the lensing arcs follows this pattern, with a visible light distribution that matches models of massive ellipticals. Its brightness in surveys placed it in the category of luminous red galaxies, chosen precisely because of their prominence across cosmic distances. The central galaxy's structure is revealed through careful photometric studies. By analysing its surface brightness profile, astronomers can determine how its light falls off, with distance from the centre. The profile matches that of other giant ellipticals, steep near the core and gradually flattening outward. Embedded within this light are clues to its formation history. Faint shells and distortions sometimes betray past mergers, the remnants of smaller galaxies torn apart and assimilated. In the case of this system, the smoothness of the light suggests that the galaxy has reached a relatively stable state after a long history of growth. Its stars, numbering in the hundreds of billions, orbit within the gravitational field of both visible and invisible matter, moving along paths shaped by the combined mass. Spectroscopic studies add further detail. The absorption lines in the galaxy's spectrum indicate the presence of old metal-rich stars consistent with the history of early formation, followed by gradual enrichment. The velocities of these stars, measured through Doppler shifts, reveal the gravitational potential in which they move. The higher the velocity dispersion, the more massive the galaxy must be to keep them bound. In this galaxy, the stellar velocities are extraordinarily high, confirming that it contains far more mass than typical ellipticals. These measurements complement the lensing data, providing two independent confirmations of its immense mass. Together, they establish the galaxy as one of the heaviest individual galaxies studied in detail. The colour of the galaxy reflects its stellar population. Unlike blue star-forming systems, the red hue arises from stars that are cooler and longer lived. Massive hot stars burn quickly and die young, so their absence indicates that star formation ceased long ago. What remains are stars with long, main-sequence lifetimes, still glowing billions of years after they were born. These stars fill the galaxy with a steady reddish glow, lacking the bright knots of star-forming regions. Observations confirm that the galaxy is quiescent with little or no cold gas left to spark new stellar births. This quiescence is typical of giant ellipticals which have exhausted or lost their star-forming fuel. The host galaxy's halo extends outward far beyond the visible arc of stars. Though faint, this halo contributes to the gravitational potential that bends background light. Its stars are old and sparse, drifting in wide orbits that carry them far from the core. Such halos are thought to form from the remnants of smaller galaxies, absorbed during mergers, their stars scattered to great distances. By studying the faint outer light, astronomers trace this history of assembly. In the lensing galaxy, the halo is broad and diffuse, another sign of the many past events that built it to its current size. Within this halo, globular clusters may still orbit ancient star groups that predate even the galaxy itself. Their presence, if detected, would add further evidence of its age and mass. Dark matter is also an integral part of the host system. The lensing arcs provide strong evidence that the visible stars alone cannot account for the gravitational field. The galaxy must be embedded in an enormous dark matter halo, invisible yet essential. This halo not only explains the lensing, but also stabilizes the motions of stars in the outer regions. Without dark matter, the stars would not remain bound at the velocities observed. The halo extends well beyond the visible light, encompassing a volume far larger than the luminous galaxy. It is this combination of stars, gas remnants, and dark matter that produces the total mass required to bend light into a near-complete circle. Despite its great size, the galaxy appears relatively calm. Unlike quasars, where matter falls rapidly into the central black hole and produces brilliant radiation, this system shows no sign of extreme activity. Its light is steady without the bright nucleus that signals active accretion. This quiet state suggests that the central black hole, though massive, is not currently consuming large amounts of gas. Instead, the galaxy exists in a stable phase, its stars orbiting in equilibrium and its central engine lying dormant. Such calmness is not unusual for giant ellipticals, many of which harbour dormant supermassive black holes that flare only when new material is supplied. The structural properties of the host galaxy thus reveal a history of mergers, star formation, and gradual quiescence. Its sheer size and mass place it among the giants of the cosmos, while its role as a gravitational lens confirms the depth of its gravitational field. Every observation points to the same conclusion. This is not an ordinary elliptical, but one of the most massive known. Its stars, its halo, and its dark matter combine to create a system capable of bending light into arcs, and at its heart lies the source of even greater gravity still hidden deeper within. From the perspective of astronomy, the journey now moves closer from the scale of stars and halos toward the Central Bulge, where mass concentration reaches its peak. Surrounding the main body of the host galaxy is an extensive stellar halo, a vast region where the density of stars gradually thins but never truly vanishes. These halos are among the faintest and most elusive components of galaxies, yet they hold critical clues to their assembly history. The stars in such halos are ancient, many of them born in small galaxies that were later consumed by the central giant. As mergers unfolded over billions of years, Stars were torn from their original orbits and flung outward, settling into the diffuse outskirts. In this way, the halo becomes a record of countless collisions and accretions, its stars lingering far from the bright core. The halo of the system producing the Cosmic Horseshoe lens is no exception. It stretches well beyond the luminous central body, tracing the enormous gravitational influence of the galaxy and its invisible dark matter companion. Measurements of halos rely on deep imaging, often pushing the limits of telescopes to detect light barely above the background sky. For massive ellipticals, these halos can extend hundreds of thousands of light-years, far beyond the central glow. Their brightness decreases with distance, but careful stacking of observations reveals their faint signature. In the case of this system, the halo is both broad and dense, consistent with the extreme lensing it produces. Its sheer size suggests that the galaxy has undergone a long history of growth, incorporating many smaller systems along the way. Each merger leaves behind stellar debris, which mixes over time into a smoother distribution. The stars of the halo are typically metal-poor, meaning they contain fewer heavy elements than those in the core. This difference reflects their origins in smaller, less evolved galaxies that merged with the giant. Globular clusters are often embedded within halos orbiting far from the center. These compact groups of stars are some of the oldest structures in the universe, forming soon after the earliest galaxies took shape. In giant ellipticals, the number of globular clusters can be enormous, numbering in the tens of thousands. Their distribution provides further insight into the mass and size of the halo. If present in this galaxy, they would serve as test particles moving through the gravitational field and tracing its extent. Their dynamics could help confirm the dark matter profile inferred from lensing. Though faint and small compared to the overall galaxy, globular clusters are powerful markers of its history and composition. The stellar halo does more than provide evidence of past mergers. It also contributes to the gravitational potential that bends background light. While most of the lensing power comes from the dense central regions, the extended halo adds a measurable effect. Its stars may be sparse, but together with the dark matter that surrounds them, they deepen the gravitational well. This is why lensing arcs sometimes extend farther than the visible core of the galaxy, reaching into regions dominated by halo mass. In the Cosmic Horseshoe, the arcs are broad and sweeping proof that the halo's influence extends across large distances. The halo thus acts as both a historical record and a present contributor to gravitational lensing. Spectroscopy of halo stars, when possible, reveals another layer of information. Their chemical compositions differ from those of the central population, often showing lower metallicity. This supports the scenario of hierarchical growth where small primitive galaxies are accreted by larger ones. The mixing of stars of different origins builds a complex stellar population in the halo, contrasting with the more uniform metal-rich stars near the core. Observing these stars requires powerful instruments, for they are faint and dispersed. Yet each spectrum adds a point to the broader picture, confirming that halos are the remnants of galactic cannibalism over cosmic time. The dark matter halo surrounding the galaxy is even more extensive than the stellar one. Unlike stars, dark matter does not thin into invisibility, but maintains a smooth extended profile that can reach far beyond the luminous boundary. The mass inferred from lensing cannot be explained without such a component. The dark halo not only accounts for the strength of the arcs, but also stabilizes the motions of halo stars and globular clusters. Its presence ensures that even at great distances from the center, stars remain bound to the galaxy. In this system, the lensing signal indicates that the dark halo is exceptionally massive, enveloping the galaxy in a sphere of invisible gravity. Without it, the stellar halo would disperse, and the arcs of light would not curve into a nearly complete ring. The dynamics of halo stars are another tool for measuring galactic mass. By studying their velocities, astronomers determine how the gravitational field changes with distance. The faster the stars move at large radii, the more mass must be present to hold them. Observations of other ellipticals show that their velocity dispersions remain high, even far from the core, implying vast dark halos. Though detailed measurements of halo stars in this system are challenging, the lensing arcs themselves confirm the same conclusion. The halo is vast, heavy, and essential for understanding the galaxy's structure. The existence of such halos connects directly to cosmological models. Simulations of galaxy formation in a universe dominated by dark matter predict that large galaxies should form through repeated mergers with halos built from disrupted satellites. The properties of halos observed today, from their sizes to their metallicities, match these predictions. In this sense, the stellar and dark halos are not anomalies but expected outcomes of cosmic evolution. What makes the halo of this galaxy remarkable is its sheer scale, commensurate with the gravitational power needed to produce the Cosmic Horseshoe lens. From Earth, the halo cannot be seen with the naked eye or even ordinary telescopes. Its stars are far too faint, their glow spread too thin across the sky. Yet their existence is undeniable, inferred from the arcs of light and the high velocities measured in the core. The halo is both real and hidden, a component that only reveals itself through careful study. Its importance lies not in its visibility, but in its role as the binding envelope of the galaxy, the region where the accumulation of cosmic history is written into the motions of stars. In this way, the stellar halo of the lensing system tells a story of growth, mergers, and unseen mass. It shows how galaxies become giants not in a single event, but through billions of years of accumulation. Each star in the halo is a witness to that history, shining faintly from a place far removed from the bright center. Together they trace the outermost reaches of the galaxy's gravity, providing both context and confirmation of its extraordinary mass. From here the focus begins to narrow again, turning from the broad halo toward the deeper role of invisible matter, whose contribution surpasses even that of stars and stretches across the entire galactic structure. Beneath the glow of stars and the faint reach of the stellar halo lies an even greater component that cannot be seen directly. This is the dark matter halo, a vast and invisible structure that outweighs the luminous content of the galaxy many times over. While stars and gas reveal themselves through light, dark matter interacts only through gravity, shaping the distribution of galaxies and their internal motions without emitting radiation of any kind. The existence of dark matter was first inferred through the unexpectedly high speeds of stars in galaxies and galaxies in clusters, speeds too great to be explained by visible mass alone. Later, gravitational lensing provided even stronger confirmation, showing that enormous amounts of unseen matter must be present to account for the deflection of light. In the lensing system that produces the Cosmic Horseshoe, the evidence is unambiguous. The mass required to bend light into such a symmetric and extensive arc far exceeds the contribution of stars. It can only be explained by a dominant halo of dark matter, extending well beyond the luminous body of the galaxy. This halo is not a separate object, but an integral part of the galaxy's structure. It forms a sphere of gravitational influence surrounding the visible stars, stretching hundreds of thousands of light-years or more. Simulations of galaxy formation in a universe filled with dark matter predict such halos, showing how small fluctuations in the early cosmos grew into large clumps. Gas fell into these clumps, cooled and formed stars, but the bulk of the mass remained dark. Over time, mergers and accretions built larger and larger halos with galaxies forming at their centers. The halo of this system is one of the largest inferred, consistent with its extraordinary gravitational strength. Without it, the arcs of the horseshoe would be smaller and fainter, unable to reach the dimensions observed. The density profile of dark matter halos has been studied in detail through both simulations and observations. Near the center, the density rises steeply, creating a deep gravitational well that governs the motions of stars. Farther out, the density declines gradually, though it never truly vanishes. This gradual decline is why halos extend far beyond the visible boundaries of galaxies. In the case of the horseshoe lens, the profile required to reproduce the arc matches well with theoretical expectations, providing further evidence that the standard model of cosmology correctly predicts the form of dark matter structures. The shape of the arc also offers clues to the symmetry of the halo. A nearly circular arc implies that the mass distribution is close to spherical, while distortions would indicate elongation. The clarity of the horseshoe suggests a relatively smooth, symmetric halo surrounding the central galaxy. Dark matter not only explains lensing but also influences the evolution of the galaxy itself. By providing additional mass, it helps stabilize the system against disruptive events. It binds stars in the outer halo, prevents gas from escaping easily, and increases the depth of the potential well in which the central black hole resides. In clusters, dark matter halos of individual galaxies merge into even larger halos, binding entire clusters together. In this sense, dark matter is the glue of cosmic structure, from the largest scales of superclusters to the cores of individual galaxies. The galaxy producing the Cosmic Horseshoe demonstrates this role clearly. Its dark halo is essential both for its lensing effect and for its stability, as one of the most massive ellipticals known. Observationally, the halo's presence is revealed not only through lensing, but also through stellar dynamics. The high-velocity dispersion of stars in the core indicates a mass far larger than what the luminous matter alone could produce. Extending this to larger radii models require a halo of dark matter to explain how stars and globular clusters remain bound at such speeds. Without the dark halo, the stars would drift away, and the arcs of light would not curve so dramatically. The consistency of results across independent methods strengthens confidence in the conclusion. This system is dominated by dark matter, and its halo is among the heaviest inferred for any galaxy. The role of dark matter halos extends beyond individual galaxies to the formation of large-scale structures. In cosmological simulations, galaxies like this one are nodes, within vast filaments, their halos connecting and merging over time. These models predict that the most massive black holes should reside in the deepest potential wells where dark matter density is greatest. Observations of this lensing system align with that prediction. The sheer gravitational power inferred from its arc suggests not only a massive galaxy, but also a central black hole of exceptional size. Thus, while the halo itself is invisible, its gravitational reach points directly toward the extraordinary concentration of matter at the center. Another aspect of dark matter halos is their role in shaping the history of mergers. As smaller halos fall into larger ones, their galaxies are drawn inward and eventually disrupted. The stars become part of the larger halo while their dark matter merges smoothly into the bigger structure. This process explains the extended nature of the halo observed here. Over billions of years, it has absorbed countless smaller systems, building up its mass and smoothing its distribution. Each event deepened the gravitational potential, increasing the lensing strength. The current halo is therefore a cumulative product of cosmic time, not a static entity, but the result of continuous growth. From Earth's perspective, the dark halo can never be seen directly. No telescope can capture an image of it, and no spectrum reveals its presence. Yet the evidence from arcs of light and stellar velocities is overwhelming. The halo is as real as the luminous galaxy, though its nature remains one of the deepest mysteries of physics. Whether it consists of undiscovered particles or something more exotic is not revealed by lensing alone. What lensing does show beyond doubt is the scale of its mass and the reality of its gravitational power. In the case of the Cosmic Horseshoe, this power is immense bending photons that have travelled for billions of years into shapes visible across the night sky. In contemplating the dark halo, one sees both the unseen foundation of the galaxy and the broader puzzle of the universe. Dark matter constitutes most of the mass in the cosmos, yet its identity remains unknown. Galaxies like this one provide natural laboratories where its effects are magnified and measurable. Each arc of light is a tracer of its presence, each velocity measurement a confirmation of its role. The halo surrounding the horseshoe lens is not unique in kind, but it is extraordinary in scale. It demonstrates how much of the universe is invisible, detectable only through gravity. This realization sets the stage for an even deeper step inward from the broad embrace of the halo to the concentrated bulge at the galaxy's core, where the density of stars and the gravitational field become strongest. Moving inward from the outskirts of the halo, the structure of the galaxy grows steadily denser until the starlight becomes a continuous glow rather than faint scattered points. This inner region, known as the bulge, is the heart of the elliptical system. Unlike spirals, which have a central bulge embedded within a rotating disk, ellipticals are essentially all bulge. Their stars orbit in random directions, creating a spheroidal structure without the ordered motion of disks. In massive ellipticals, such as the one that forms the Cosmic Horseshoe lens, the bulge is immense, holding hundreds of billions of stars packed into a space only tens of thousands of light-years across. This dense stellar concentration creates the bright core visible in imaging surveys, the central glow that dominates the profile of the galaxy. The bulge is dominated by old stars, primarily long-lived low-mass ones that shine with a reddish hue. Their light, when blended together, gives the galaxy its luminous red classification. Spectroscopic measurements show that these stars have relatively high metallicities compared to those in the halo. This indicates that they formed later after several generations of star formation enriched the gas with heavier elements. Such enrichment points to an active past when the galaxy's predecessors formed stars at high rates before merging into the present giant. Today, however, the bulge is quiescent. The lack of cold gas means that star formation has nearly ceased leaving the galaxy to shine with the steady light of ancient populations. The motions of stars within the bulge provide one of the clearest measures of mass. Through spectroscopy, astronomers detect the Doppler shifts of stellar absorption lines, which reveal how quickly stars move toward or away from Earth. By compiling these velocities, they build a velocity dispersion profile showing the spread of stellar motions. In normal galaxies, these velocities are modest. In the bulge of this system, they are extraordinarily high, exceeding hundreds of kilometers per second. Such speeds can only be maintained if the gravitational potential is deep, requiring a mass far beyond the visible stars. The bulge thus becomes a laboratory for testing the mass distribution, confirming what lensing already indicated: this galaxy is among the most massive known. The density of stars in the bulge affects its appearance. At the very centre, the light profile steepens, rising sharply toward the core. This central concentration is sometimes called a cusp, though in the most massive galaxies it can flatten into a core where stellar densities are slightly lower than expected. These central structures are shaped by the history of mergers and the influence of the black hole at the center. Binary black holes formed during mergers can eject stars from the core, creating a deficit of light. Whether the bulge of this particular system shows a cusp or a core remains a subject for detailed observation, but its brightness profile clearly places it among the most massive ellipticals. Embedded within the bulge are traces of past activity. Though the galaxy is quiescent today, faint signatures of ancient starbursts or merger-induced star formation can linger in the stellar populations. By studying the distribution of metallicities and stellar ages, astronomers reconstruct this history. Many of the stars in the bulge are older than 10 billion years, formed when the universe itself was young. Others may be slightly younger, added through later mergers. Together they create a composite population that reflects billions of years of growth. The uniform red colour seen in wide-field surveys is the blended light of all these stars shining steadily in the absence of new star formation. Gas and dust are scarce in the bulge. Unlike spirals where dust lanes thread through the disk and gas clouds feed new stars, massive ellipticals have lost or exhausted their reservoirs of cold gas. Some of this gas was consumed in past star formation, while other portions were heated during mergers or expelled by energetic processes in the core. As a result, the bulge is largely free of obscuration, its stars visible without the interference of dust. This clarity makes it easier to measure its light profile and stellar dynamics, though it also means that opportunities for ongoing star formation are limited. The absence of gas further emphasizes the galaxy's mature state, one in which evolution has slowed to a quiet glow rather than a vigorous blaze. Despite the apparent calm, the bulge exerts a profound gravitational influence. It binds stars in random orbits, supports the structure of the galaxy, and contributes to the overall lensing signal. The bulk of the galaxy's visible light comes from this region, making it the most prominent feature in images. Yet beneath the glow lies an even greater concentration of mass. The velocity dispersion of stars near the center hints at the presence of something far more massive than stars alone could account for. The bulge is not just a collection of ancient stars, but also the gateway to the innermost region, where the central black hole resides. The study of bulges in galaxies has revealed consistent relationships between their properties and those of their central black holes. In particular, the mass of the black hole correlates with the velocity dispersion of stars in the bulge. This correlation, known as the M-sigma relation, suggests that the growth of black holes and bulges is connected. As galaxies merge and bulges grow, their central black holes also gain mass through mergers and accretion. In the most massive ellipticals, the black holes reach extraordinary sizes far beyond those in smaller galaxies. The bulge of the Cosmic Horseshoe galaxy, with its extreme velocity dispersion, points directly toward the presence of one of the heaviest black holes known. The bulge's structure also affects the distribution of dark matter in the inner regions. While the halo dominates at large radii, the bulge and black hole dominate near the center. This layered structure means that different components control gravity at different distances. Observations of lensing arcs, stellar motions and gas dynamics together map out this distribution, showing how stars and dark matter combine to shape the bulge. In this galaxy, the balance is tilted strongly toward mass concentrations at the core, consistent with the gravitational power needed to bend light so dramatically. The bulge therefore represents both an endpoint and a transition. It is the endpoint of galactic growth, where mergers and star formation have produced a vast quiescent population of stars. But it is also the transition zone leading to the black hole at the very center, where mass is concentrated into a region far smaller than the galaxy itself. By studying the bulge, astronomers trace the path from the diffuse halo to the compact core following the gradient of density that culminates in the unseen central object. From the arcs of light at the outskirts to the dense stars of the bulge, each step inward confirms the extraordinary mass of the system and prepares the way for the study of its deepest core. Inside the bright bulge of the galaxy, traces of interstellar matter still remain, though they are far more limited than in systems where star formation is ongoing. In spirals, clouds of gas and dust dominate the inner regions, feeding a cycle of birth and death as stars form and explode. By contrast, in massive ellipticals, the reservoirs of cold gas have long been depleted or expelled. What lingers is often hot, thin plasma, and a scattering of dust grains material heated to such high temperatures that it radiates primarily in X-rays. Observations of similar galaxies reveal halos of hot gas trapped by gravity extending well beyond the visible stars. These halos may reach temperatures of tens of millions of degrees Kelvin, too hot to cool efficiently into star-forming clouds. The same conditions are likely present in the host of the Cosmic Horseshoe, where the bulk of the interstellar medium is in a high-energy state, contributing little to new star formation, but adding to the galaxy's overall gravitational field. Dust, though less prominent, can sometimes be detected even in these massive systems. Infrared observations have shown faint emission from small amounts of cooler material, often remnants of past mergers or minor accretions of gas-rich companions. In the Cosmic Horseshoe galaxy, any dust is faint compared to the brightness of its stars, yet its presence cannot be ruled out entirely. Dust can obscure starlight, scatter photons, and re-radiate energy at longer wavelengths, affecting measurements of stellar populations. In cases where dust lanes are present, they often appear as narrow, irregular features cutting across the otherwise smooth glow of the galaxy. Whether subtle dust structures exist here requires extremely sensitive imaging, but if they do, they would provide evidence of past interactions with smaller galaxies that delivered fresh material. The dynamics of gas and dust, even in such small amounts, are shaped by gravity and the potential for interaction with the central black hole. Gas that cools and sinks toward the center can provide fuel for accretion-sparking activity that may temporarily light up the galaxy's core. In the present state of this system, however, the absence of a bright nucleus suggests that very little gas is currently reaching the central engine. Instead, the hot halo and quiescent bulge prevent large-scale inflows. Feedback processes in the past, possibly driven by earlier active phases of the black hole, may have heated or expelled much of the gas that could otherwise have fed star formation. This interplay between black hole activity and gas supply is thought to be one of the main reasons why massive ellipticals remain dormant today. The scarcity of gas does not mean a complete absence of activity. Hot plasma in the galaxy can radiate X-rays detectable by space observatories. Such emissions confirm the presence of gas even when it's invisible in optical images. In many massive ellipticals, this hot gas is seen extending beyond the visible stars trapped by the combined gravity of stars' dark matter and the central black hole. Its temperature and distribution provide insight into the depth of the potential well. In the case of the Lensing galaxy, the hot gas contributes to the overall mass balance, though its fraction is small compared to stars and dark matter. The presence of such gas is another sign of the galaxy's maturity, its material no longer able to condense into cool, star-forming clouds. Small amounts of cooler gas, if they exist, could be revealed through radio observations of molecular lines such as carbon monoxide. These lines trace cold, dense regions where stars might still form if conditions allowed. In some giant ellipticals, faint signals of such molecules have been detected, often linked to minor mergers that supplied fresh gas. In the Cosmic Horseshoe system, any such reservoirs are likely to be minimal. The lack of blue young stars in its spectrum supports the conclusion that star formation is effectively shut down. The interstellar medium here is not a driver of growth, but a residue of past processes shaped by gravity and heated by time. The absence of abundant gas has consequences for the future of the galaxy. Without fuel, it cannot sustain significant new star formation, meaning its stellar population will continue to age and redden. Over billions of years, the stars will evolve, some becoming white dwarfs, neutron stars, or black holes. But the overall luminosity will fade slowly as no new bright young stars replace those that die. This passive evolution is characteristic of giant ellipticals, which shine primarily with the light of aging stars. The lack of dust and gas also means that little obscuration affects observations, allowing a relatively clear view of the bulge and core. The dynamics of the remaining gas are still tied to the central mass. Even a small inflow toward the core could, under the right conditions, reignite activity around the central black hole. Such episodes are thought to occur sporadically in dormant galaxies when chance interactions supply new material. For now, the galaxy appears quiet with no evidence of an active nucleus. But its history suggests that periods of intense activity may have occurred in the past, leaving behind imprints in the heating of the gas and the suppression of further star formation. This feedback cycle, in which the black hole influences the galaxy at large, is one of the central themes of galaxy evolution. The interstellar medium also plays a role in the gravitational lensing signature, though only indirectly. By contributing to the overall mass of the galaxy, gas adds to the gravitational potential that bends light. However, its fraction of the total mass is small compared to stars and especially dark matter. The arcs of the Cosmic Horseshoe are shaped primarily by the combined mass of stars' dark matter and the unseen black hole at the center. Gas and dust are secondary players, their influence visible mainly through emission at different wavelengths. Thus, in moving from the bulge toward the core, the observer finds an environment increasingly stripped of raw material for star formation. The interstellar medium exists in hot diffuse form, contributing more to the galaxy's equilibrium than to its growth. Dust and cooler gas are scarce faint relics of a past that was far more dynamic. The present-day galaxy is defined by stability rather than change, its mass locked into stars, its gas heated beyond usefulness, and its core lying dormant. This quiet scene belies the tremendous concentration of matter hidden within a concentration that becomes evident not through radiation but through gravity. As the journey inward continues, attention shifts to the region immediately surrounding the black hole, where matter under the right conditions can still fall inward, producing the accretion features that reveal the central engine. At the very center of the galaxy, the gravitational field becomes so steep that any gas or dust drifting inward faces a dramatically different environment from the calm outer halo. Here lies the region often referred to as the Accretion Zone, where matter can spiral inward under the influence of the black hole's pull. Even though the galaxy appears quiescent today, the structure of this zone is fundamental to understanding its central dynamics. In active galaxies, accretion produces some of the brightest phenomena in the universe, as gas falling inward heats up to millions of degrees Kelvin and radiates across the electromagnetic spectrum. In dormant systems like the one that shapes the Cosmic Horseshoe, the accretion zone is faint, yet its role remains central to interpreting the overall mass distribution. The process of accretion begins when gas, whether from stellar winds, the hot halo, or captured companions, loses angular momentum and drifts inward. As it approaches the black hole, it forms a disk-like structure flattened by rotation and friction. This accretion disk is heated by both compression and friction, causing it to radiate intensely when enough material is present. Around stellar mass black holes, such disks can produce X-rays detectable even in nearby galaxies. Around supermassive black holes, they can generate luminosities that outshine entire galaxies, creating quasars. In this galaxy, however, the lack of strong radiation indicates that the accretion disk is either absent or operating at a very low level. Any matter that does approach the black hole must be accreting inefficiently, producing little visible output. Despite this low activity, the accretion environment is not empty. Hot plasma from the galaxy's halo can occasionally flow inward, providing a slow trickle of material. Stars orbiting close to the center may shed mass through stellar winds, some of which is captured by the black hole. This steady faint supply maintains a potential reservoir for accretion, even if it does not currently ignite the kind of brilliant activity seen in quasars. The evidence for such a low-level inflow is inferred from the balance of gas dynamics and the need to account for occasional weak emissions. In any case, the physical principles governing accretion are universal matter that falls too close cannot escape, and in the final stages it crosses the event horizon, vanishing from view. Accretion processes are shaped by gravity but also by magnetic fields and turbulence. In rotating disks, magnetic fields can create instabilities that drive angular momentum outward, allowing material to fall inward. These processes explain how gas, which would otherwise orbit stably, is able to spiral toward the center. Even when accretion rates are low, the underlying physics remains active with friction and magnetic stresses redistributing energy. The result is a dynamic but faint environment waiting for the supply of material to increase. If a merger or gas inflow were to occur in the future, the central black hole could reignite, transforming the quiet galaxy into a luminous, active nucleus. For now, it rests in a subdued state, its accretion zone present but relatively dark. Evidence of past accretion may linger in the structure of the galaxy itself. Feedback from the black hole in the form of winds or jets can heat gas and regulate star formation. In many giant ellipticals, cavities have been observed in the surrounding hot plasma, carved by outbursts of energy in earlier epochs. Such signatures testify that even dormant systems once experienced active phases. Though direct evidence in the Cosmic Horseshoe galaxy is limited, its lack of cold gas and quiescent state suggests that past feedback played a role in suppressing future star formation. The black hole's influence extends beyond the event horizon, shaping the evolution of the entire galaxy. The accretion zone is also the region where astronomers find indirect evidence for the black hole's mass. Stellar orbits near the center are sensitive to the gravitational pull of the unseen object. By measuring how fast these stars move, astronomers infer the presence of a central mass far larger than can be explained by stars alone. This method has been applied successfully in other galaxies such as the Milky Way, where individual stellar orbits confirm the mass of the central black hole. In the case of the horseshoe lens, velocity dispersions measured across the bulge point to the same conclusion: an enormous central object must be present. While direct imaging of individual orbits is not possible at this distance, the integrated effect on stellar motions provides robust evidence. The relationship between the accretion zone and the galaxy's larger-scale dynamics is also critical. The depth of the gravitational potential ensures that even small amounts of inflowing gas can be captured. The dark matter halo and bulge both funnel material toward the center, though the lack of available gas today limits the scale of inflow. In the past, mergers would have delivered large reservoirs of gas fueling bright activity and rapid black hole growth. Each such episode would have expanded the accretion disk-driven strong feedback and increased the mass of the central object. The current quiet phase is therefore the outcome of billions of years of intermittent feeding, during which the black hole grew to extraordinary size. Theoretical models of accretion help explain the differences between quiet and active galaxies. When accretion rates are high, disks become thin, bright, and radiatively efficient. When accretion rates fall, the disks can transition into hot, thick flows known as radiatively inefficient accretion flows. These flows produce little visible light even while matter continues to fall inward. It is likely that the black hole at the center of this system exists in such a low-efficiency state today, quietly accreting without producing a luminous nucleus. This interpretation aligns with observations showing no bright, active galactic nucleus, despite the galaxy's immense mass. The presence of an accretion environment, however faint, highlights the connection between the smallest and largest scales in the galaxy. From the diffuse halo of dark matter spanning hundreds of thousands of light-years down, to the innermost accretion zone, only light hours across every layer contributes to the galaxy's structure. The accretion zone is the final stage of this inward journey, where matter succumbs to gravity's ultimate pull. Even if it is quiet today, its significance cannot be overstated, for it is here that the extraordinary black hole reveals itself most clearly through its gravitational influence. Thus, while the galaxy as a whole appears calm, the very center holds the potential for activity that could alter its state dramatically. The accretion zone may now be subdued, but its physics continues to govern the fate of any matter that drifts too close. It is the threshold to the event horizon, the place where ordinary processes of galactic dynamics end, and the realm of extreme gravity begins. From here, the exploration must focus on the scale of the black hole itself, where measurements derived from stellar motions and lensing arcs converge to reveal one of the heaviest objects ever detected in the cosmos. The challenge of weighing a black hole lies in the fact that it cannot be seen directly. It emits no light of its own, and in galaxies where accretion is quiet, there is little surrounding radiation to betray its presence. Instead, astronomers rely on the movement of matter around it, using stars' gas and light as traces of gravity. For the galaxy that produces the Cosmic Horseshoe lens, such methods have provided one of the most compelling measurements of central mass ever achieved. By combining stellar velocity dispersions with the geometry of gravitational lensing, astronomers have inferred the presence of a black hole whose size places it among the heaviest ever recorded. The logic is straightforward. The faster stars move near the center, the deeper the gravitational well must be. Lensing adds a second line of evidence showing how strongly the galaxy curves space-time. Together they yield a consistent conclusion that the central object is extraordinarily massive. One of the key techniques is stellar dynamics. By observing the absorption lines in the spectrum of the galaxy, astronomers measure how wide these lines appear. The broadening arises because stars move at different velocities along the line of sight. A high velocity dispersion means stars are moving very quickly in random directions. In the bulge of this galaxy, dispersions reach several hundred kilometers per second values so high that they cannot be explained by stellar mass alone. When models account for both visible stars and dark matter, an additional unseen central mass is still required. This mass, concentrated in a region far smaller than the galaxy itself, matches what theory predicts for a supermassive black hole. Another approach involves detailed modeling of the gravitational lens. The shape and extent of the horseshoe arc depend not only on the overall mass of the galaxy, but also on how that mass is distributed. By fitting the observed arc with models that include a central point-like concentration of mass, astronomers test whether the data are better explained with or without a black hole. In this system, the inclusion of a central black hole improves the match significantly, confirming that its presence is necessary. The combined evidence from lensing and stellar dynamics leaves little doubt the galaxy hosts an object of truly extraordinary mass at its center. The size of this black hole is expressed not in physical dimensions but in mass compared to the Sun. While the Sun's mass defines the scale of ordinary stars, black holes at galactic centers can reach millions or billions of solar masses. The black hole in their horseshoe lens belongs to the upper extreme of this distribution, measured in tens of billions of solar masses. This places it in the rare category of ultramassive black holes, a group so heavy that only a few confirmed examples exist. The precision of the measurement arises from the unique combination of lensing geometry and stellar motion, two independent checks on the same gravitational field. The method of inference does not reveal the black hole itself, but the results are robust. No other explanation fits the data as well. A cluster of dark objects such as neutron stars or smaller black holes could not remain stable over cosmic timescales, and the density required exceeds what ordinary matter can sustain. The only plausible interpretation is a single supermassive black hole dominating the core of the galaxy. Its mass is concentrated within a radius smaller than a few light days, an almost unimaginable compression of matter. The curvature of space-time around it is so extreme that nothing, not even light, can escape once past the event horizon. The measurement techniques applied here have been refined over decades. In the Milky Way, astronomers tracked the orbits of individual stars near the center to confirm the presence of a black hole 4 million times the mass of the Sun. In nearby galaxies, gas dynamics and stellar dispersions have revealed black holes up to a few billion solar masses. In the case of the horseshoe lens, the distance is too great for direct stellar orbits to be observed, but the combination of velocity dispersions and lensing geometry provides a powerful alternative. The results extend the range of known black hole masses upward, demonstrating that nature produces objects even heavier than once imagined. The implications for galaxy evolution are significant. The mass of the black hole correlates with the mass of the bulge, suggesting that as galaxies grow through mergers, their central black holes grow alongside them. The black hole in this system fits this pattern, lying at the extreme end where the most massive galaxies harbour the most massive black holes. This correlation suggests a feedback mechanism in which energy released by accretion regulates both star formation and black hole growth. Even though the galaxy is quiet today, its past must have included episodes when the black hole consumed large amounts of matter, radiating enormous energy into its surroundings. Those episodes would have shaped the evolution of the galaxy, heating gas, suppressing star formation, and contributing to its present quiescent state. Measuring such a massive black hole also tests the limits of current theories. The formation of objects of this scale requires sustained growth over billions of years. Either they began as relatively large seed black holes in the early universe, or they grew through repeated mergers and accretion events. While the details of this process remain uncertain, the existence of ultramassive black holes like this one proves that such growth is possible. Their rarity suggests that only galaxies in the most favorable environments, such as dense clusters with abundant material, can reach such extremes. The Cosmic Horseshoe galaxy, located within a region of high mass concentration, fits this scenario well. The reliability of the measurement rests on the consistency of independent lines of evidence. Stellar velocity dispersions require a deep gravitational potential. Lensing arcs confirm that the mass is centrally concentrated. Both point to the same conclusion: the central black hole is tens of billions of solar masses. Though indirect, the convergence of methods gives confidence. Such measurements are among the most precise tools available for probing the invisible. In the absence of direct light, gravity remains the universal signal shaping the paths of both stars and photons. Thus, the inference of the central black hole's mass marks a turning point in the inward journey, from the broad arcs of lensed light to the faint stars of the halo from the old populations of the bulge, to the rare traces of gas, every layer has pointed toward the same outcome, an extraordinary concentration of mass at the very centre. The measurement techniques used here confirm what the arc suggested from the start. The galaxy not only bends light into a horseshoe, but also houses one of the heaviest supermassive black holes ever found, its gravity extending across scales from light years to billions of years of stellar history. From here the focus narrows further onto the true scale of this black hole and how it compares with others across the known universe. Among the catalogue of known supermassive black holes, most fall within a range of a few million to a few billion times the mass of the Sun. These objects are already extreme by any standard, anchoring the centres of galaxies and shaping their long-term evolution. Yet there exists a smaller group that lies far beyond this typical scale. The black hole inferred at the heart of the galaxy, producing the Cosmic Horseshoe lens, belongs to this rare category, with a mass measured in tens of billions of solar equivalents. This places it among a handful of ultramassive black holes that challenge the upper limits of current understanding. Its scale can be appreciated only by comparison. The black hole at the centre of the Milky Way, known as Sagittarius A, contains about 4 million solar masses. The black hole in the nearby giant elliptical Messier 87, famous for being imaged directly by the Event Horizon Telescope, weighs about 6.5 billion solar masses. Another record holder, TON 618, reaches more than 60 billion solar masses. The object in the Horseshoe Lens galaxy, with a measured weight of around 36 billion solar masses, is therefore not only exceptional, but one of the heaviest whose mass has been confirmed through multiple methods. The rarity of such objects reflects the conditions required for their growth. In the early universe, black holes formed from the collapse of massive stars. These initial seeds may have contained only a few tens or hundreds of solar masses. For them to reach billions, they must have grown rapidly through accretion of gas, or through mergers with other black holes. Growth by accretion alone faces limits, because radiation produced by the infalling gas pushes back against further inflow. To reach ultramassive scales, periods of unusually efficient growth, or successive mergers between already massive black holes, are likely necessary. The presence of such an object in the Cosmic Horseshoe galaxy implies that its history included a series of major mergers, each delivering not only stars and gas, but also central black holes that combined into a larger whole. Over billions of years, this cumulative process built the extraordinary mass observed today. Astronomers classify black holes into categories depending on their size: stellar mass, intermediate mass, supermassive, and ultramassive. While stellar mass black holes form directly from stars, ultramassive ones represent the extreme upper end of galactic evolution. Their presence suggests that nature has no strict limit on how large these objects can become, though practical limits may arise from the availability of fuel and the timescales available for growth. The existence of the 36 billion solar mass object in the Horseshoe Lens demonstrates that galaxies in the right environments can nurture central engines of unprecedented scale. Few galaxies, however, provide the conditions for such growth. Dense environments, frequent mergers, and abundant material in earlier epochs appear to be necessary ingredients. The comparison with other giants underscores the significance of this discovery. While Messier 87 and TON 618 are well-known benchmarks, the Horseshoe Lens black hole confirms that multiple galaxies in the universe have reached similar extremes. Each measurement strengthens the case that ultramassive black holes are real and not anomalies. They may not be common, but their existence has consequences for understanding both black hole physics and galaxy evolution. In particular, they help set the boundaries of the M-sigma relation, showing how far the correlation between bulge velocity dispersion and black hole mass can be stretched. By lying at the high end of this relation, the horseshoe lens system demonstrates that the same principles apply even at extraordinary scales. The size of the event horizon of such a black hole is another way to appreciate its mass. For a 36 billion solar mass black hole, the event horizon would span a region larger than the orbit of Pluto around the Sun. Light that ventures within this boundary cannot escape, and the curvature of space-time there is extreme. Although the black hole itself cannot be imaged directly at this distance, theoretical models allow astronomers to estimate the size of its horizon. Such calculations highlight the immense scale of the object, a region of no return measured in light days rather than kilometers. This boundary is not a physical surface, but a point of no escape, beyond which gravity dominates absolutely. Despite its enormous size, the black hole today appears dormant. Unlike quasars where accretion floods the environment with radiation, the horseshoe lens galaxy shows no signs of intense nuclear activity. This quiet state does not diminish the black hole's mass, but rather highlights its current lack of fuel. In earlier epochs, when gas was more abundant, it may have shone as a brilliant quasar visible across the cosmos. Today, the absence of cold gas means that it rests in silence detectable only through its gravitational influence on stars and light. This transition from active to dormant phases is common among giant galaxies, which often harbour massive black holes that flicker between activity and quiescence depending on available material. The extraordinary weight of this black hole places it within a small group that helps define the upper bound of known cosmic structures. These ultramassive objects provide tests for theories of galaxy and black hole coevolution. Do they form from the earliest, most massive seeds, or do they build up gradually through repeated mergers? Do they influence their surroundings differently from smaller black holes, shaping galaxies in unique ways? Each measurement adds to the effort to answer these questions. The horseshoe lens black hole stands as one of the clearest cases its mass established through both lensing and dynamics, two methods that converge on the same conclusion. The presence of such an object also has implications for the environments in which galaxies reside. Black holes this heavy are typically found in the centers of massive ellipticals that themselves lie within dense cosmic neighborhoods. The Cosmic Horseshoe system matches this expectation, positioned within a region rich in matter and surrounded by structures that suggest a long history of mergers. Its black hole is therefore not only an individual anomaly, but part of a broader pattern, linking environment, galaxy growth, and central mass. By studying these connections, astronomers refine their understanding of how the larger structures in the universe come to be. Ultimately, the black hole at the heart of this galaxy exemplifies the extremes of cosmic evolution. Its mass size and quiet state encapsulate billions of years of history, from initial collapse to sustained growth. It is an endpoint of galactic development, representing what happens when conditions align to feed a black hole continuously over cosmic time. Though rare, such ultramassive black holes remind us that the universe is capable of producing structures on scales that defy ordinary comprehension. The Cosmic Horseshoe galaxy offers one of the best documented examples, a system where arcs of light stellar speeds and theoretical models all converge to reveal a central object of unparalleled weight. From this extraordinary core, the exploration can turn now to its present condition, a black hole of extreme mass that nevertheless shows a surprising calm, its energy output subdued despite its gravitational dominance. The black hole at the center of the horseshoe lens galaxy, though extraordinary in scale, does not currently radiate with the brilliance of an active quasar. Instead, it appears calm, its surroundings devoid of the luminous accretion features that often betray the presence of such a massive engine. This apparent stillness is not unusual for giant ellipticals. Many of them harbour supermassive or ultramassive black holes that remain quiescent for long periods, flaring into activity only when new material becomes available. The absence of bright jets or strong emission lines suggests that the central object in this system is accreting very little gas at present. Despite this dormancy, its gravitational pull dominates the galaxy's core, binding stars in rapid orbits and shaping the motion of matter across tens of thousands of light years. This calmness can be deceptive, for it hides a turbulent past. To reach a mass of 36 billion suns, the black hole must have consumed vast quantities of material. In earlier epochs, when gas was more abundant and mergers more frequent, it likely shone as a quasar radiating with a luminosity thousands of times that of its entire host galaxy. During those active phases in falling matter would have formed a hot accretion disk producing intense radiation across ultraviolet and X-ray wavelengths. Jets of relativistic particles may have erupted from its poles, streaming outward for hundreds of thousands of light years. Such episodes could have profoundly influenced the galaxy's evolution, heating gas and preventing it from cooling into star-forming clouds. What remains today is the quiet aftermath of those violent times, a galaxy stabilized by feedback from its central engine. The present quiescence does not mean the black hole is inactive. Even when accretion rates are low, faint emissions can sometimes be detected. Low-level radio signals, weak X-ray glows, or subtle infrared features may hint at ongoing but minimal feeding. These emissions, though faint, confirm that the physics of accretion never truly halts. It merely operates at reduced efficiency. Astronomers studying such dormant giants gain valuable insight into how black holes transition between active and quiet states. The Horseshoe Lens galaxy provides one of the most extreme examples, with a central mass large enough to dominate its core, yet an output faint enough to blend into the stellar background. Stability at this scale results from a delicate balance. Without abundant cold gas, the black hole lacks the fuel to reignite as a bright quasar. The hot halo surrounding the galaxy holds material at temperatures too high for efficient accretion. Occasional stars wandering too close may be disrupted, their material feeding the black hole in short bursts, but such events are rare. In the meantime, the black hole rests in equilibrium, its gravitational influence extending silently outward. The stars of the bulge orbit under its pull, their motions providing the key measurements that reveal its mass. The arcs of lensed light shaped by the galaxy's total gravity provide another confirmation. Both lines of evidence converge to show that the central object remains a giant regardless of its outward appearance. The calmness of this black hole contrasts with the spectacular displays seen in more active systems. Quasars in the early universe, for example, blazed with luminosities that outshone entire clusters of galaxies. Some of those quasars are thought to host black holes as massive as, or even more massive than the one in the Horseshoe Lens. Their activity reflects a cosmic era when fuel was abundant and black holes grew rapidly. Today, in the quieter cosmic present, many of those objects have settled into dormancy. Their brilliance has faded, leaving behind massive silent cores detectable only through gravitational signatures. The Horseshoe Lens galaxy is therefore not an anomaly, but a natural stage in the life cycle of ultramassive black holes. This quiet state has implications for the surrounding galaxy. Without active feedback, the hot gas in the halo radiates slowly in X-rays, but no new bursts of energy prevent it from cooling further. Yet the mass of the galaxy and its black hole still maintain a high-energy environment, keeping the gas too hot to condense into star-forming clouds. The result is a stable quiescent system, its stars aging quietly, while its central mass rests in silence. Such stability may last for billions of years unless disturbed by a major merger or fresh inflow of gas. If such an event occurs, the black hole could awaken, briefly reigniting as an active nucleus before returning once more to dormancy. Comparisons with other massive galaxies reinforce this picture. Messier 87, though hosting an active jet, spends most of its time in a relatively quiet state compared to the most luminous quasars. Other giant ellipticals show similarly subdued behavior. The horseshoe lens system fits into this pattern, differing mainly in the sheer scale of its central mass. It exemplifies how ultramassive black holes can remain hidden in plain sight, detectable only through the motion of stars and the bending of light. Their quietness makes them challenging to study, yet their very mass ensures they cannot be ignored. The quiet state also serves as a reminder that luminosity is not a measure of importance. The absence of radiation does not lessen the gravitational impact of the black hole. Its pull shapes the galaxy from the core outward, setting the velocities of stars, influencing the distribution of gas, and controlling the balance of forces in the bulge. Even dormant, it remains the dominant force in its environment. This invisible influence is what allows astronomers to weigh it with such confidence. The very fact that it does not shine brightly simplifies certain measurements, letting the steady starlight of the bulge serve as a clean probe of gravity without interference from glare. Thus, the stability of the horseshoe lens galaxy today represents a stage of cosmic balance. The black hole has reached a size where its growth has slowed, star formation has ceased, and feedback has left the galaxy quiescent. All the evidence points to a system in equilibrium, immense in scale, yet subdued in appearance. The calm masks the extraordinary journey that produced it, and the potential for future change should circumstances shift. For now, the black hole rests as a silent anchor, one of the most massive objects ever measured, exerting influence, not through light, but through gravity alone. From this recognition, the path of exploration narrows further still, focusing on the physical limits that govern such extreme masses, and the boundaries of physics that define what can and cannot occur at the threshold of the event horizon. Gravity in the central regions of galaxies reaches an intensity that pushes the limits of physical theory, and in systems like the horseshoe lens galaxy, those limits are tested at their extreme. The black hole at its core, measured in tens of billions of solar masses, provides an environment where even familiar processes behave differently. Stars orbit at extraordinary speeds, their paths shaped not by the combined pull of visible and dark matter, but by a single compact object whose density surpasses anything else in the galaxy. The deeper one moves into this region, the more dominant the black hole becomes, until all other contributions to gravity are negligible. At this scale, the governing equations are those of general relativity, and Newtonian approximations no longer suffice. Time and space are curved so sharply that conventional intuitions about motion, distance, and energy lose meaning. Within a few tens of thousands of light years, the stellar bulge contributes significantly to the gravitational field. Closer in, within a few hundred light years, the black hole becomes the controlling mass. Stars in these regions move on random but rapid orbits, their velocities a direct measure of the central mass. The velocity dispersion can reach several hundred kilometers per second, evidence of the deep gravitational well. If one could isolate individual stars in the immediate vicinity, as has been done in the Milky Way, their orbits would trace ellipses or rosettes around the invisible core with periods of years to decades. At the distance of the horseshoe lens galaxy, such individual orbits cannot be resolved, yet the collective effect appears in the broadened absorption lines of its integrated spectrum. That broadening encodes the presence of an object whose gravity is far beyond that of ordinary matter. The black hole's influence is not confined to the motion of stars. It also affects the dynamics of gas dust and plasma in the central region. Even in a dormant state, when little material is available to accrete, any gas that strays too near is accelerated to high speeds and heated by compression and friction. If enough gas were present, it would form an accretion disk glowing brightly in ultraviolet and X-ray bands. The absence of such emission in this system indicates that the inflow is currently minimal. Still, the theoretical framework of accretion physics applies. Viscosity within the disk driven by magnetic turbulence transfers angular momentum outward and mass inward, allowing gas to spiral down toward the event horizon. The closer it gets, the hotter it becomes until at last it crosses the horizon and disappears from the observable universe. The event horizon of a 36 billion solar mass black hole is enormous by human standards, with a radius measured in light days. This boundary is not a physical surface but a region of space-time from which light cannot escape. Inside, all paths curve inexorably toward the singularity. General relativity predicts that matter and energy reaching the singularity are compressed into infinite density, though what this means physically remains unknown. The singularity is a point where equations break down, not a place that can be probed directly. What astronomers can observe is limited to the region outside the horizon, where gravity's pull warps the paths of photons and shapes the orbits of matter. Despite the extremity of these conditions, the physics outside the horizon can be studied with remarkable precision. The bending of light around the black hole, known as gravitational lensing on much smaller scales, produces observable effects in systems closer to Earth. In principle, the black hole in the Horseshoe Lens galaxy would produce similar distortions of nearby starlight, though at its distance such details are beyond reach. What remains measurable is the broader imprint stars moving faster than can be explained without an unseen mass arcs of light from background galaxies shaped into near circles, and the stability of a galaxy core bound by gravity of extraordinary strength. The concept of limiting physics arises here. The maximum densities achievable before collapse, the maximum luminosities producible by accretion, and the maximum rates of growth allowed by radiation pressure all become relevant. For a black hole of this size, accretion at the so-called Eddington limit would produce light equal to the combined luminosity of trillions of stars. If such an object were actively accreting, it would be visible across vast stretches of the universe. The fact that it is not means that its current accretion rate lies well below this theoretical maximum. Still, the limit itself defines a boundary that cannot be crossed. If too much gas falls in too quickly, the resulting radiation pushes back, preventing further inflow. The existence of such a balance is what allows black holes to grow steadily over cosmic time without consuming everything instantly. Another limit arises from the interplay of black hole growth and galaxy evolution. The feedback from an actively accreting black hole heats and expels gas, curtailing further star formation and reducing the fuel available for additional accretion. This feedback loop ensures that black holes and their host galaxies evolve together, maintaining the correlations observed today. In the case of the Horseshoe Lens system, the extreme mass of the black hole implies that feedback must have been powerful, in the past regulating the galaxy into its current quiescent state. The quietness observed today is not a lack of activity, but the result of physical limits imposed by gravity radiation and the finite supply of matter. At these scales, physics also encounters open questions. What happens at the singularity where density and curvature diverge remains unsolved. Theories of quantum gravity attempt to address this, but no consensus exists. While general relativity describes the space-time outside the horizon, with extraordinary accuracy, it leaves unanswered what occurs inside. The black hole in the Horseshoe Lens galaxy is far beyond reach for direct exploration, but its existence highlights the challenge. Physics as currently known reaches its boundary at the event horizon and breaks down at the singularity. These limits are not failures but markers of where deeper theories are needed. The black hole's quiet stability today is therefore framed by these physical boundaries. It is massive enough to dominate its environment, yet limited by the laws of radiation pressure and feedback. It can grow further if new material becomes available, but its growth will always be constrained by the balance of forces. Its density is extreme, but not infinite outside the singularity. The space-time it shapes is describable, but not the final collapse within. In this way, the object represents both the culmination of known physics and the threshold of the unknown. The Horseshoe Lens system demonstrates this vividly. Its arcs reveal mass on galactic scales. Its stars confirm velocity dispersions far above the ordinary. Its core hides a black hole whose properties push against the limits of theory. Yet for all this extremity, the system is stable, calm, and in equilibrium. Nothing in its present state violates physical law. Instead, it occupies the edge of what those laws permit a natural outcome of billions of years of cosmic evolution. In following the journey inward from the cosmic web to the event horizon, one arrives here at the boundary where explanation gives way to limits, and where gravity rules absolutely. At the innermost edge of the galaxy, just outside the event horizon, lies the final region accessible to observation. This is the sphere where photons skim the boundary of escape, where matter spirals at nearly the speed of light, and where time slows relative to distant observers. The scale of this region for a 36 billion solar mass black hole is vast compared to stellar mass counterparts, yet it is still tiny relative to the size of the galaxy. Its radius is measured in light days, a compact domain, when set against a host that spans hundreds of thousands of light years. Here the distinction between ordinary and extreme ceases to hold, for the physics is governed by general relativity alone. Space is curved so tightly that even the paths of photons loop around the black hole before emerging toward distant telescopes. Although the galaxy is not an active quasar today, the geometry of this region can still be inferred from theory. In black holes of any mass, three characteristic zones exist: the event horizon, the photon sphere, and the innermost stable circular orbit. The event horizon marks the point of no return. The photon sphere defines where light can orbit in unstable loops, and the innermost stable orbit sets the boundary for matter to circle safely before plunging inward. For a black hole of this mass, these distances are scaled up enormously, but the proportions remain the same. Gas or stars that wander too close cross these thresholds and vanish, their information lost to outside observers. It is in this sense that the horizon is not a surface, but a boundary in space-time. Even in quiet galaxies, occasional stars can drift into the influence of the central black hole. If a star ventures within a certain radius, tidal forces can tear it apart in what is known as a tidal disruption event. The debris may briefly form an accretion disk, producing a flare of radiation detectable across great distances. For an ultramassive black hole, the tidal radius lies very close to the event horizon, meaning many stars can be swallowed whole without disruption. This reduces the likelihood of bright flares, contributing to the apparent quietness of such giants. The black hole in the Horseshoe Lens system may therefore consume matter, silently adding to its mass without producing observable outbursts. Around the event horizon, space-time itself rotates if the black hole possesses spin. In theory, this creates an ergosphere, a region where particles cannot remain at rest relative to distant space. Instead, they are dragged along with the rotation of space-time. In smaller active systems, this effect is linked to the launching of relativistic jet streams of plasma, propelled outward at near light speed. For the black hole here, no such jets are visible today, but the potential remains. If sufficient matter were to flow inward, and magnetic fields became organized, the spin of the black hole could once again power enormous outflows. For now, the absence of visible jets emphasizes the dormant state of the system. The event horizon scale also defines the ultimate measure of mass for this black hole. Its size cannot be deduced by light, but by the gravitational effects on stars and on background galaxies. These indirect measurements converge on the conclusion that the horizon is vast yet hidden. Its presence is undeniable, but its nature is concealed by definition. No information from inside escapes, and no observation can reveal the singularity itself. What astronomers detect is the edge of influence, stars moving faster than expected, arcs of light bent into curves, and galaxies distorted by the curvature of space-time. Together, these effects confirm that the horizon exists, and that its mass is among the heaviest ever measured. In practical terms, the event horizon defines the limit of exploration. Beyond it, no data can be recovered. This limitation does not diminish the significance of the discovery, but rather underscores it. The journey inward from the cosmic web through clusters and halos, through bulges and gas, ends here at the boundary of knowledge. Everything observed points consistently toward the same conclusion. The black hole is ultramassive, calm and dominant. Its gravitational field defines the galaxy's center, its halo and its lensing power. It is both an object and a region of space-time inseparable from the laws that govern gravity at its most extreme. The scale of such an object challenges comprehension. To imagine a sphere of no return wider than the orbit of Pluto set within a galaxy, hundreds of thousands of light-years across, is to confront the immensity of cosmic structures. Yet it is also to recognize that even such extremes are natural outcomes of physics applied over billions of years. From the collapse of the first stars to the growth of galaxies, through mergers, from the feeding of black holes by gas to their quiet dominance in old ellipticals, the process leads inevitably to such endpoints. The black hole in the horseshoe lens system is one such endpoint, a silent giant revealed not by light but by gravity. Thus, the inward journey reaches its conclusion at the event horizon, the ultimate boundary. No step can go further, for space and time curve inward beyond reach. What remains is the recognition of structure, scale, and balance. The galaxy stands as one of the most massive known, its arcs of lensed light proof of its density, its stellar speeds, proof of its depth, and its central object proof of nature's capacity to form extremes. At the final threshold, observation ceases, but knowledge holds firm. The black hole remains unseen, yet everything around it confirms its existence, its size, and its power. Here at the horizon, the exploration rests, having traced the path from the cosmic web to the innermost boundary of one of the heaviest supermassive black holes ever found.